Physical vapor deposition, known as PVD for short, is a vacuum deposition technique used to produce very thin film coatings onto a variety of substrates. By thin film, we mean in the nanometer scale, up to the level of a few microns. The technique is characterized by phase transitions directly from a solid target material into a vapor, which then condenses onto the substrate surface. So we use PVD because it's an excellent technique for depositing materials which can't be coated in a liquid form, and it can't be really put into a solution with a solvent either. This is generally for high precious metals such as gold, also aluminium and oxide, various ceramic oxides. The technique is flexible and scalable. It can be used for an extremely wide variety of materials. It's an advantageous method to use both at the research lab and at the industrial scale due to the precise films it can create. It's been applied to a number of different fields, including decoration, thin films, fabrication, and research. Now, there's two main types of PVD that PI-KEM supports: evaporation and sputtering. We supply coating materials for both techniques, as well as equipment such as crucibles and sputter coaters. The choice of technique between those two really depends on the material that's being coated and whether the coating needs to be deposited upside down or top down. In general, evaporative deposition uses energy to vaporize the material, which then condenses onto the substrate surface. This is in two main types of thermal evaporation and electron beam, also known as E-beam evaporation. The main differences between them is the energy source responsible for the heating, and which method is better generally depends on the coating material. We supply a wide range of materials for evaporative coating, with key material groups being precious metals, base metals, alloys, and ceramic oxides. We can supply these materials in a variety of forms, such as pellets, granules, lumps, foils, and discs. All materials can be supplied to an extremely high purity, and our excellent supplier relationships allow us to deliver consistent and uniform batches, ensuring reproducibility. Key point for thermal evaporation is that the material needs to be homogeneous before the evaporation begins. This prevents the coating material from spitting, which is when individual particles get far greater amount of energy, which can't be spread more evenly into other parts of the coating, and it essentially explodes, and you have far tinier, hotter particles spitting all over, and then you don't get an even coating on your substrate. Pellet or granule material is first melted inside a crucible. However, filling the crucible with uniformly melted material can be quite laborious, costly in time and material. So instead, a starter charge can be used, which is preformed to the shape of the crucible. The absence of void spaces allows the material to be used far more quickly, and it's ultimately a much more cost-effective solution. In general, all materials should be conditioned before use. Evaporating off the first layer of atoms removes any potential surface contaminants from going onto your substrate. So the benefits and applications of evaporation, it has a wide range of applications, including depositing optical coatings such as mirrors, filters, and reflective coatings. It's used in photovoltaics such as transparent conducting oxides, thin film electronics such as OLED screens, metallization of surfaces for electrical contacts and packaging. It also has uses in aerospace and in thin film research. Overall, evaporation is an invaluable technique for creating thin and uniform films. It must be conducted within a strong vacuum and is best suited to materials with low melting points. Evaporation produces precise film thicknesses and works well on flat substrates. The technique offers a high and efficient deposition rate, and the system is generally simpler and lower cost than sputtering.